say generally the AC signals are given as sinusoidal signals. So when it comes to the half wave rectifier, only one diode will be used, and we'll have the transformer where the primary of the transformer is connected to the power supply, which we get to our houses, and then the transformer secondary is connected to the diode, and here the transformer, whatever transformer we are using, it is a step down transformer. So 230 volts will be the strength of the input signal is reduced here. Okay, so using the secondary of the transformer, we are trying to convert the AC signal to the DC signal. So here we have used one diode. Okay, so for the positive half cycle, for the negative half cycle, we have tried to analyze the circuit. So when it is for the positive half cycle, the diode will become forward biased because P will get connected to positive and N will get connected to the negative terminal. So because of which the diode will be forward biased, and for the ideal diode case, we'll consider that forward biased diode as short circuit. So we have short circuited the diode, and we have tried to analyze in the sense we have also seen the mathematical equations here. So the load current, load current we have calculated, and at the same time load voltage also we have calculated. Okay, so that is what your equation which have represented here. Okay, then comes case 2. In the case 2, like as I've already mentioned, the generally AC signals are given in the form of sinusoidal signals. So we have just analyzed for the positive half cycle. In the same way, we need to take it for we need to analyze for the negative half cycle as well. Okay, so when you take the negative half cycle, the diode will become reverse biased. So generally the reverse biased junction or the reverse biased diode can be replaced with the open. So when we open it, there won't be any current flow. So current through the load will be equal to 0, and at the same time the output voltage across the load will also be equal to 0. VL and V0 will be equal to 0, and the same equation it is represented mathematically, like IL is equal to Im sin omega t from 0 to pi, and it is 0 from pi to 2 pi, and V0 is nothing but Vm sin omega t from 0 to pi, and pi to 2 pi it is 0. So this is what we have seen in the last class. So here what we have done, we have analyzed the circuit, and we have got the once again. Just reconnect my digital pad. Okay, so what so we have seen, if you just look at the waveform, it is not the pure DC. Okay, pure DC in the sense it should have some constant value throughout. Okay, but here if you observe, it is not pure DC, it is the pulsating DC. Pulsating DC in the sense it will have both AC component and the DC component present in it. Okay, so since I have both AC component and DC component present in it, I need to find out what is the efficiency of this particular half wave rectifier. Okay, and so many other mathematical terms I need to find here, so that I will be able to find how efficiently or how good the half wave rectifier is rectifying its AC signal to DC signal. So so the first thing is I need to find the efficiency. Okay, so in order to find the efficiency, generally efficiency is given by gamma is equal to PDC, output power by input power, PAC by PDC. So generally current power is given by VI or I square R. Okay, so I DC square by RL load, across the load we are finding. In the same way, this PDC will be equal to I RMS, because AC quantity, if I have the AC quantity, I'll not be able to find the exact its effective value, because AC signal, it is not constant, so it is varying signal. Okay, so since it is varying signal, at different times will have different values. So that is the reason what we'll do, we'll try to find the RMS value for that AC quantity. So IRMS square into RL will give me the AC power. So in order to find this, I need to calculate what is the DC current and what is the RMS value of that signal. Okay, so in order to find this, first we'll go with the first mathematical equation. Let us find IDC, average or DC value of load current. DC value of load current. So here what I need to do, I need to find IDC. Okay, because if I want to find the efficiency will be always calculated as output by input. Okay, so here we'll be taking output power by input power. So output power is nothing but it is in the form of DC current. Okay, so DC, I need to find what is the DC value. So for that reason, I need to find the average value. Average value is also said to be the DC value. Okay, DC value of load current. Okay, so now what I need to do, where is that waveform? This is my waveform. Okay, so this is the load current. Okay, so for this load current from 0 to 2 pi in one cycle, I need to find the DC value present in this. DC value can also be found by taking the average value. Okay, and here if you observe, see if I have 1, 2, 3, 4, something like this, some real values like this, I can just add all of them and divide it by the total number. Okay, that will give me the average value. But here if you observe, it is not the case. It is a AC signal, like AC signal in the sense it is not constant. Okay, constant values. So you have infinite number of values from 0 to pi. Okay, so what you need to do, you need to take the integration. Integration is another form to find the area under this. Okay, so what we'll do is, in order to find DC, we will take IDC is equal to, or I average value. Okay, anything is fine. Okay, I average and IDC both are same only. Okay, so IDC will be equal to, I need to find the average value only. Okay, so average value in the sense I need to find the area under the curve. Okay, area under the curve. Area under the curve, because here it is not DC signal, or it is not the constant values which I can add and divide it by total number. Okay, so instead I need to go with the integration here. Okay, integration in the sense I have to find the area under the curve. Okay, divided by time period. Okay, so if you observe, the time period is 2 pi. Okay, so T, time period is nothing but 2 pi here. Time period is nothing but 2 pi. Okay, so I need to find the area under the curve. Area can be found by using the integration. Okay, so hope you know very well, like finding the integration is nothing but finding the area under that. Okay, so I need to take area for complete cycle. See, I have got one complete cycle in this way. This is my IL output. Okay, and the maximum value is Im sin omega t. Im sin omega t is the waveform representing this from 0 to pi, and pi to 2 pi it is 0. Okay, and the maximum value is nothing but Im. Im is the maximum value of this load current. Okay, so here what I need to do, I need to find area under the curve. Okay, so from 0 to 2 pi, I need to find the area. So what is the, see, if I want to find the area, I need to know equation representing this particular waveform. Okay, it is nothing but Im sin omega t. Im sin omega, or let me just write as load current IL d omega t divided by total time period. It is nothing but 2 pi. Okay, so I need to find the area under this IL curve. Okay, area under this load current divided by time period. Okay, so now but if you observe, from 0 to pi I have different thing, and pi to 2 pi I have different thing. So what was the equation representing this? See, from 0 to pi I have Im sin omega t. From pi to 2 pi it is 0. Okay, so what I need to do, I need to split the integration here. Okay, so I can write 1 by 2 pi, anyway it is constant, let me take it out. So I'll write as 0 to pi IL d omega t plus pi to 2 pi IL d omega t. I need to just split the integration in this way. Okay, so this will be equal to 1 by 2 pi integral 0 to pi Who is this? Okay, fine, let me continue. Oh, hope you people are following me, right?
Yes, ma'am.
Anywhere you're getting any doubt, please let me know. Okay, so here I have to take area under the curve IL. Okay, so for that I'm taking over one period from 0 to 2 pi, and now here I'm splitting the integral. Okay, so from 0 to pi, the equation what we have got was Im sin omega t. So let me just show you once again if you want. So you better note it down along with me. Okay, so IL is nothing but Im sin omega t from 0 to pi, and it is 0 from pi to 2 pi. So the same thing I'll substitute here. Okay, Im sin omega t d omega t plus integral pi to 2 pi. IL value is 0 there, d omega t. Okay, so now what I need to do, I need to just see, anyway Im is a constant, I can take it out. Im integral 0 to pi sin omega t d omega t plus, anyway this is 0. Okay, so this will be equal to 1 by 2 pi, sorry, Im by 2 pi. Now what is the integration of sine? What is the integration of sine? Integral sine minus cos omega t, and the upper and lower limits are 0 to pi. Okay, so now I need to substitute this upper limit and the lower limit. So Im by 2 pi is nothing but minus, I'll take common, so cos pi minus cos 0. Okay, so it is nothing but Im by 2 pi into minus cos pi is, what is cos pi?
Sine.
Cos pi is nothing but 180 degrees. Cos 180 is
1
minus 1. Minus 1. Okay, so you know this, right? All silver tea cups. Okay, hope you know, all of you know this. Okay, cos pi minus cos 0. So cos pi is minus 1 minus cos 0 is 1. Okay, so just simplify this. Just simplify this. You'll have, this will be equal to Im by 2 pi into minus 2 into minus, it is 2. So 2 will get cancelled. It is Im by pi. Im by pi is nothing but your IDC value. Okay, IDC, I average, both mean the same only. I average, but this I corresponds to the load current. Okay, Im by pi. This is what your IDC. In the same way, if I want to find VDC, okay, load DC load voltage, DC load voltage, then it will be DC load voltage. VDC is nothing but how will you calculate VDC in general? V is equal to IR, right? So VDC is nothing but IDC into RL. Okay, so IDC is nothing but Im by pi into RL. But if you just recall, or I'll just show you, what is it? Vm by RL is nothing but Im. Okay, Vm by RL is nothing but Im. So let us replace Im with Vm by RL. So this will be equal to Im. Im is nothing but Vm by RL. We know that. Okay, here only I'll write. We know that Im is nothing but Vm by RL. So substitute 1 in 2 or B in A. Okay, so here VDC will be equal to Im by pi. Sorry, Im in place of Im, I have to replace it with Vm by RL into pi into RL. So this and this will get cancelled. So I'll be left out with Vm by pi. So VDC, the load current, the DC current is nothing but Vm by pi. Okay, so IDC is nothing but Im by pi and VDC is nothing but Vm by pi. So this is the average current or average voltage across your load. Okay, so this is nothing but the DC value that is present in the DC current that is present in the output whatever we have got. Okay, hope this is clear to all of you. Anybody have got any doubts in the simplification can ask me. Okay, and one more thing I want to tell you. See, if you understand half wave rectifier, full wave rectifier will also be the same. Okay, only thing is with respect to the equations, it will change. Okay, there you'll have the output for both half positive half cycle and the negative half cycle. That is only difference. Okay, otherwise rest all derivations will remain same. Okay, so make sure that even if you're not understanding, let me know, I will repeat it. Okay, but make sure that you understand all the derivations now itself. Anybody has got doubts, please ask me. Any doubts here? Is it clear to all of you how we have taken the equation? See, all these derivations are very, very important. Either you take for the sake of internal or for the sake of external. It is very, very important. Hope all of you are following. Are you all following? Am I going fast?
No, ma'am.
Okay.
No.
Okay. Are you all understanding? Amandeep?
Yes, ma'am.
Is it clear, ma'am?
Yes, ma'am.
Okay. So others also, others. Amruta? Amruta R.
I'm understanding, ma'am.
Okay. Amruta R. Amruta A.
Understanding, ma'am.
Okay. Others also. Everybody in the class. Arpita BM. Anil BA. Anil. He's on hold. Arpita BM. Arpita BM. Arpita, are you there, ma? Arpita, last call for you, ma. Are you there? Arpita?
Yes, ma'am.
Why you not responding then? Network issues, ma'am. Right? This is what the answer you'll be giving me? Arpita?
No, ma'am.
Am I audible to everybody?
Yes, ma'am.
Yes, ma'am.
Okay. So is this clear? Are you all understanding? Have you all understood the derivation? Anybody want me to repeat? I'll go in this way. Anybody want me to repeat anything? Anybody want me to repeat anything?
No, ma'am.
Okay, fine. Okay, so we have got the DC value. Okay, so as I've already mentioned, this whatever output we have got, it is not the pure DC. It is the pulsating DC. Pulsating DC in the sense it will have both AC component and as well as DC component present in it. Okay, so now I need to find the effective value of this particular output waveform. Okay, so why we will generally calculate effective value? Anybody knows? See, if it is like if you just observe the waveform, it is not the pure DC signal. Okay, so what? So it is having the AC component present in it. AC component is nothing but changing in the output values based on the time. Okay, based on the time the output will vary. That is nothing but your AC values. Okay, so here if you observe, it is a AC value. It is having both AC as well as DC. Why I'm saying that it contains DC also, because the average value is not equal to 0. If it is equal to 0, then I can say that there is no DC present in this, but here it is not the case. Okay, there is a AC component as well as DC present in that, because I have shown you also IDC, whatever we have found, it is not equal to 0. If it was equal to 0, then I would have said that it is like there is no DC component present in this. Okay, so since I have AC values, generally for the AC values, we will not be able to identify what is its effect on the circuit. So in that case, what we'll do, we'll find the RMS value. Okay, So hope you people would have learnt in basic electrical also, right? Related to the RMS value. Effective value or RMS value. So can anybody tell me how to find the effective or RMS value? So you know the significance, right? You understood the significance. What is the use of finding RMS value? So again here I need to find effective or RMS value of load current. Load current. As well as load voltage also. If I find one, I can find the other one. So load current. So it is IRMS. I need to find the RMS value of the load current. So can anybody tell me how to find the average, effective value of any signal? Whatever you have learned, you can tell me, ma, because I really don't know what exactly you have learned with respect to the RMS value in your basic electrical. But I know that these all concepts you would have learned in basic electrical, but how you related your RMS value, I really don't know. So if you know anything related how to find RMS value, you can tell me. If you don't know, you tell me, I will only explain you.
Imax by root 2.
Imax by root 2, it is for the sinusoidal signal. Any sinusoidal signal, so this is what my sinusoidal signal, right? So any sinusoidal signal, the RMS value will be Im by root 2 or Vm by root 2. If it is in terms of, if it is for voltage, it will be Vm by root 2. If it is for current, it will be Im by root 2. This is a value. I'm asking you what is a procedure to find RMS value. I'm happy that you at least know this, but I just want you to tell me the procedure. Okay, fine. So for the sinusoidal signal, you have said that, let me consider it is a current waveform only. So for current waveform, it is Im by root 2. So how will you get this value? Is my question. See, whatever questions I'll be asking, it will be all related. Okay. So can anybody tell me how you'll get this value Im by root 2? Have you calculated it in your basic electrical? Have you calculated any time?
Yes.
Okay, fine. Anyway, I don't know whether you have learned it or not. Let me just teach you. So root RMS is nothing but root mean square. Root in the sense I need to take square root. Mean in the sense I need to take average. Square in the sense I need to square the waveform. Okay, so how will I find this? See, everything is in the what is that, name itself. I need to take the mean first. Okay, I need to take the square. See, as I've already mentioned, if it was real values, okay, real values like 1, 2, 3, so one, like let me take an example, 1, 2, 3, 4. So these are the real values. So what I can do, I can just take square of each term, okay, divided by average in the sense 1, 2, 3, 4 under root. Okay, if I take this, I will get the RMS value of this particular quantity. But here it is not the case because I have the sinusoidal signal. Okay, so since it is a time varying signal, in specific it is a time varying signal. So what I need to do, I need to take square of the square, and see, I cannot just take the square. See, because this is what the waveform, for this only I'm finding the RMS value. So I need to take each and every point. So each and every point in this is I need to take area, okay, and square of each point and area under that. Okay, so that is given by integral 0 to 2 pi IL square d omega t, and mean value, so 2 pi and square root. Okay, so root mean square. This is how anything you take, any waveform, either the triangle waveform or square waveform, whatever might be the waveform, this is a procedure. Okay, so you need to take square, integrate it. Okay, because if you take this this signal, it is still a kind of sinusoidal signal only, and like it is time varying signal only. Okay, so what you need to do, you need to take the area of the square, mean value, and under root. Okay, so always the root mean square value will be found in this way only. Okay, so if you just take your sinusoidal signal, okay, so for complete cycle from 0 to 2 pi, you need to take the square of each and every point. In the sense, you need to find the area of that square term and mean. So 0 to 2 pi under root. Okay, so let me just go ahead with this. So this will be equal to 1 by 2 pi. I will take it outside. So it will be 0 to 2 pi. Okay, 0 to pi. Let me take separately because the equation what we have got, we know that. Okay, let me write that equation first. This is a general formula. Whatever I have written here, this is a general formula. Now we know that IL is nothing but Im sine omega t from 0 to pi and is equal to 0 from pi to 2 pi. Okay, so here IL value is different from 0 to pi and pi to 2 pi, so I have to split the integration. So IRMS is equal to root of 1 by 2 pi. I'll write I'll split the integral 0 to pi IL square d omega t plus integral pi to 2 pi IL square d omega t. Okay. So the next step will be under root of 1 by 2 pi. So as I've already shown you here, from 0 to pi my signal is Im sin omega t, but from pi to 2 pi it is 0. So let me substitute that 0 to pi Im sin omega t whole square d omega t plus integral pi to 2 pi, it is 0 d omega t. Okay, so let me just take this under root of 1 by 2 pi. Im whole square will be Im square I can take out, so I'll write this as Im square integral 0 to pi sin square omega t d omega t. See, until here whatever I have substituted here, until here you have the concept. After this it is normal integration. So I think you all are very good in integrating the terms. So Im square by 2 pi. I cannot directly find the sin square omega t. So what I'll do, I'll write in terms of cos. So it is 1 minus cos 2 omega t by 2. Okay. So 2 sin square theta is nothing but 1 minus cos 2 theta. So the same thing I've used here. So d omega t. Now again we split the terms. So Im square by 2 pi. Split the terms, integral 0 to pi 1 by 2. Okay, 1 by 2, or take 2 outside, so it will become as Im square by 4 pi into integral 0 to pi 1 d omega t minus integral 0 to pi cos 2 omega t d omega t. Okay, so again you just write it under root of Im square by 4 pi. So the integral 1, it will be omega t, and you need to substitute upper limit and the lower limit, minus cos omega 2t, cos 2 omega t. What is the integration of cos? Integration of cos. What is the integration of cos? Tell me the integral cos.
Sine.
Yes, sine 2 omega t divided by 2, right? Because I have the constant also. Okay, so 2, and it is from 0 to pi. Okay, so it is equal to under root of, let me write little small, my pages got over. So this is pi minus 0 minus, see, 1 by 2, let me take outside, it will be sine 2 pi minus sine 0. Okay, so what is sine 2 pi? Im square by 4 pi into pi minus half into, what is sine 2 pi? 0. Sine 2 pi is 0. Sine 0 is also 0. Okay, so this will be equal to under root of im square by 4 pi into pi, because anyway half into 0 it will be 0 only. So this pi and this pi will get cancelled. So I will be just remain with im square by 4. So im square by 4 is nothing but im by 2. So finally I've got IRMS value is nothing but im by 2. Okay, for the sinusoidal signal it is im by root 2, but for the pulsating DC signal it is im by 2. Okay, so this is your IRMS value. Okay, any doubts here? Any doubts here?
No.
Let me just take the new one. Okay, so now we have got IRMS we have got, right? IRMS we got as im by 2. Okay, in the same way let us also find VRMS. VRMS is nothing but IRMS into RL. Okay, root mean square value of the pulsating DC. Okay, so IRMS into RL. So IRMS is nothing but im by 2 into RL. Okay, but we know that im is nothing but Vm by what is it, Vm by RL. Okay, so just substitute this in this equation. So VRMS is equal to, in place of im I can substitute Vm by RL into 2. So into RL. So this RL and this RL will get cancelled. So you will have as Vm by 2. This is your VRMS value. Okay, so I've got IRMS and I got VRMS. Now I need to find the efficiency. As I've already told, it is PAC by PDC by PAC. PDC power, DC power. Okay, DC power. DC power is given by, either you can calculate by using VDC into IDC, or you can even calculate IDC square into RL. Okay, either of these equations you can use. So IDC, we know what is IDC. IDC we have got as what is that? IDC we have got IDC we have got as im by pi. Okay, so let me substitute that. So im by pi whole square into RL. This is your PDC. Okay, so I need to find AC power also. So AC power. Okay, AC power, PAC. PAC is nothing but, as I've already mentioned, I will be using RMS values because this will give the effective values. So VRMS into IRMS. So VRMS, or I can use IRMS whole square into RL. Any of the formulas you can use. So it is nothing but PAC is nothing but IRMS. IRMS is nothing but im by 2. Im by 2 we have got, right? IRMS is im by 2. im by 2. Wait, let me just go back. im by 2 whole square into RL. Okay, so just simplify it. im square by 4 into RL. Okay, even this one PAC also, PDC also, you try to expand it. Im square by pi square into RL. Okay, so now I need to find the efficiency. So efficiency is nothing but, it is given by P DC output power by input power, P DC by PAC. PDC we have got as im square by pi into RL, pi square into RL, right? im square by pi square RL divided by PAC. PAC we have got as im square by 4 into RL. So this RL and this RL will get cancelled. This IM square and this IM square will also get cancelled. So efficiency is generally denoted with eta. Okay, efficiency is nothing but 4 by pi square. Okay, so 4 by pi is nothing but 3.14 whole square. Okay, so just find out and tell me what is the value. Take out your calculus and find out and tell me what is the value. Quickly. 4 by 3.14 whole square. Anybody has got the calci with you?
4056.
What ma? What?
0.4056.
4056. Okay, so generally efficiency will calculate in terms of percentage. So efficiency in percentage is given by efficiency in percentage is given by, you need to multiply with 100. Okay, so this is nothing but 40.5%. This is the efficiency of your half wave rectifier. So if you observe, our efficiency have got below 50%. So the efficiency is very less in half wave rectifier. So this is the disadvantage of your half wave rectifier, since it is rectifying only half of the signal. Okay, so this is what the disadvantage of your half wave rectifier. Okay, so what happens in the full wave rectifier we'll see later. Okay, so in the exam they may ask you derive the expression for efficiency and show that the derive the equation for efficiency for half wave rectifier and show that it is equal to 40.5%. So in that case you need to just derive everything whatever I have derived until now, IAC, what is it, IDC, IRMS. Okay, so this entire thing, and then finally you need to end up here. Okay, so this is the complete derivation you need to do. Okay, hope this is clear to all of you. Is it clear, ma?
Yes, ma'am.
Okay. In the see here you need to always remember the typical values. Typical values in this is like the equations, whatever you have got, IDC we have got as IM by pi. All these equations you need to remember, because in the exam they may ask you to solve the problems. So for that reason you need to what is that, Vm by pi. You need to remember all these equations. Okay, IDC is IM by pi, VDC is Vm by pi. IRMS is IM by root 2, IM by 2, VRMS is VM by 2, and finally efficiency we have got as 40.56%. Okay, all this you need to remember. Okay, still I have some more derivations to do, but until now whatever we have done I have just summarized. Okay. Anybody has got doubts until here, please make sure that you clarify it today on like now itself, because again as I've already mentioned, full wave rectifier also will be calculating all this efficiency. Still you have some other parameters to be calculated, so all this will be doing in your full wave rectifier also. So if you understand this half wave rectifier, full wave rectifier you can do easily. Okay, so that is the main reason I'm like asking you, like if you have got any doubts. Shall I go to the next derivation? Okay, shall I go to the next derivation? Nobody has got any doubts?
No.
Okay, fine. So next, ripple factor. So this class is until 12:50, right? So let me just finish this ripple factor and leave you. Okay, ripple factor. See, I have a request for you. See, when I'll be in the flow of teaching, no, I'll not even notice the time. Okay, so we have got strict orders that we need to leave you at least 10 minutes before. 10 minutes before the class. Okay, so make sure somebody take the responsibility of reminding me. Okay, because in the flow of teaching, no, I'll just forget the time. Okay, so ripple factor. Okay, so coming to the ripple factor in the sense, see, as I've already mentioned, whatever output we are getting, it is not the pure DC. Okay, so it is the pulsating DC. Okay, so pulsating DC, and it consists of both AC components and as well as DC component. Okay, so here half wave rectifier, the main aim of the rectifier is it has to convert AC signal to DC signal. Okay, so but it is not happening here properly. Okay, so the amount of AC component that is present in this pulsating DC is said to be the ripple. Okay, ripple. Okay, ripple is nothing but the amount of AC component present in pulsating DC is said to be ripple. So here I need to find out how much amount of the ripple is present. Okay, so that is given by ripple factor. Ripple factor, that is generally denoted with gamma. Okay, so here I need to find the gamma. Gamma is nothing but in RMS value of, see, always whenever it comes to the AC component, I will be taking RMS value only, because AC value, its effective value will not be known until and unless you calculate the RMS value. So RMS value of AC component present in pulsating DC given by DC component in pulsating DC. Okay, so if I am calculating with respect to the current, it will be IAC, and I need to find IAC's RMS value divided by IDC. This is what I need to find. So for this, no, if you just check the notes, I have derived the expression for that. Okay, so that much is not required. If anybody is interested, you can go through that derivation. Otherwise, directly I'll give you the formula. Okay, it is given by IRMS. This entire derivation I have derived in your notebook. Okay, so in your what is that notes, whatever I have uploaded in the Teams. See, in the Teams you can find all 5 module notes. Okay, and I can assure you that if you just go through my notes, you'll be able to attempt all 100% questions in your exam. Okay, that assurance though I can give you. Okay, so IRMS divided by IDC whole square minus 1. Okay, this is the formula we will get after so much of analysis. Okay, so I have taken some equations and then I have found the what is IAC. See here, I, whatever I have got, IL, whatever IL I have got, IL or I have denoted with I also, right? That consists of both AC component as well as DC component. So now what I need to do, I need to find the RMS of this value. Okay, divided by IDC. Okay, RMS value of this given by IDC. Only when I calculate all this, I'll get this equation. So if anybody is interested, you can just go through the derivation. I have derived everything clearly, so you can just go through it for your personal interest. Okay, that's what I'm telling you. If anybody is interested, you can just go check the derivation. Otherwise, this is the final expression. So in the exam, for the sake of exam, you need not derive the complete expression. You can directly take this formula.